All right, so what I'd like to do in this video is show you a couple things. Um, I've created this little worksheet, as you can see, and the worksheet is really kind of designed to help you understand how to read a statement that's said to you in words, some type of area or probability statement. Convert the words into mathematical symbols so that you can have a mathematical statement that represents this. Then how to shade an appropriate area with a picture, and then to find the area under that picture, to the right or left of a z-score, two different ways actually. I'd like to use this table. This is table 2 of your areas under the normal distribution. And then, of course, with your TI calculator, which kind of has this table built into it. It's just that you have to know how to use it. All right, so let's give this first question a look. So the scenario in words here says, find the area to the left of a z-score of 1.73. All right, you can tackle this a number of different ways. You can read this statement in words, and you can translate those words into symbols if you'd like. Or, what I like to do a lot of the times is I'll look at this scenario in words, and I'll look at the picture and immediately want to shade the area in the picture. So, for example, I'm going to try this. I'm going to go ahead and put a line here. And this line right there represents, 1.73. And that's a z-score, don't forget. See, on the standard normal distribution, the values on the bottom axis, the x-axis, those are z-scores for the standard normal distribution. For a plain ordinary normal distribution, one whose mean is not 0 and standard deviation is not 1, it's actually going to be, those are called raw scores and they're x values. All right, so there's 1.73, and this is saying to the left of 1.73. All right, so I'm going to do my best to shade to the left of 1.73. You got to bear with me because this works good sometimes and sometimes it doesn't play nice. So I'm going to do my best to shade. Now when we mean shade to the left of 1.73, we technically mean shade to the left forever. All right, so let's pretend that this squiggly little line here shades that entire area. All right, so there's the picture. So here's the mean of 0 in the middle. Remember, the spread from center is 1. I didn't put that anywhere in the picture, but remember, the mean is 0, standard deviation is 1. That's a z-score of 1.73. And this probability statement, I'll write it as P for probability, and I'll write Z for the z-score is less than 1.73. All right, so there's my statement in words. Let's blow that up a little bit so we can see it. Now, this statement in mathematical symbols is the conversion of this statement in words. This picture is that probability statement and this thing in words. So at this point, what you need to do now is determine what is this area. Now, how much of this area is shaded? Remember, the area under this bell curve is 1. So how much of the 1 is shaded? All right, well, I'm going to show you 2 different ways to do this. Now, hopefully you've read the chapter already. So if you read the chapter, this should be pretty easy for you. You go to your statistical tables, which I have those posted in week number 7. They're just called, the PDF is called stat tables. The first table actually is a table of NCR values. And then the second table, table 2, that's one we're in, is the normal distribution values for the areas. The first part of the table is for negative z-scores. And the second part of the table is for positive z-scores. So this this table here, as you can see, I'm going to use the positive ones because my z-score, as you can see, is positive, 1.73. And remember, this table only gives area on the left. So if you know a value, a z-score, it gives you the area to the left forever. So I did my best, as you get to see the shade my picture like this one is. All right, so all I really need to do is look up 1.73 in the z-score table. All right, so let me move this out of our way. As you can see, here's 1.7, right? That's 1.7 there. And here's the 3 up here. So you just got to follow down this column till you get to that 1.7. It looks like it's this 0.9582 value, which means that the area from this point here to the left forever, if that z was 1.73, is approximately 0.9582. The table is rounded to 4 decimal places, as you can see. As you'll see when we do the calculator, I believe it gives us to 9 or 10 decimal places, if I remember correctly. All right, so we're all set up here. This question wants the area to the left of 1.73. And, looking at this, you can see it's this value here, 0.9582. All right, so that answer is 0.9582, which, just for the record, is similar to saying 95.82%. Now, what answer should you put down? Should you say the decimal or the percentage? Well, really, it's a matter of what is the question asking you. If they just ask you for a proportion or a probability, most people would leave 0.9582. But if my stat lab, for instance, asks you for a percent, and you'll know because it'll have a percent sign. It'll have a little blank box where you fill in the box, and it'll have a percent in there. Then the question will ask you, what percent of area is to the left of 1.73 as a z-score? All right, so now there it is, pretty simple, right? All right, so now what about the next question? It says find the area to the right of this same exact z-score. All right, so let's go ahead and draw that line again. So I'm going to do my best to, mimic that picture up there. And this z-score is going to be 1.73 again. And I need to shade to the right this time. So I'll do my best to shade to the right. And once again, remember, when we shade to the right, it shades to the right forever. Remember, the bell curve never stops going in both directions. It's called asymptotic to the x-axis. It extends infinitely in both directions, and this red curve never actually touches the black bottom axis. The red bell curve kind of floats on top of that x-axis. So, it extends infinitely in both directions. So when we say find the area to the right of 1.73, we mean from this line right here, 1.73, to the right forever. How much area is that? All right, well, we already found the area to the left in the prior question, which is about 0.9582 of the entire one, don't forget. All the area is 1. All right, so this question is just really common sense. So as a probability statement, we just copy this one because it's really the same statement. All we have to do is flip the inequality symbol. All right, so this symbol right here, instead of saying less than, we'll say greater than. The probability, the z-score, is greater than 1.73. Okay, so there it is. All right, so that answer, obviously, is going to be 1 subtract that prior area. So all we're going to have to do is do 1 subtract 0.9582. All right, so let's type that in here. So 1 subtract 0.9582. All right, and that answer is 0.0418. So if you have the area on the left, you'll get the area on the right. Remember, this table here, table 2, does not give area on the right. It only gives area on the left because it's called cumulative. Cumulative, the word cumulative means from the beginning. So from the beginning, which is to the left forever, all the way up to and including the z-score you're talking about, that's what this table gives you, area on the left, because it's a cumulative table. All right, fine. The table's been around for centuries, obviously, and it's old news. When I was a kid, I took stats, back in the early '90s when I was in college, and we used this table, same table you're looking at. This calculator here came out around 93-ish, 94 when I started teaching high school, and we weren't allowed to use the calculator when I was a math major. They wanted us to use tables. Everything was kind of old-fashioned still back then. But actually nowadays, it's 2016. We use technology now. This table is in this calculator. So all I need to do is tell the calculator, hey, listen, go get me the area to the left of 1.73, and it'll go grab it for you and tell you the answer. All right, so let's talk about how to use this. Now, you already know how you've been to the probability distribution menu. You've been there already. So the probability distribution menu is above the vars key. That's where the binomial distribution is located. So if I hit second vars, looks like my calculator is not playing nice. So let me try it again. So second vars. If you go to the bottom of this list, there's the binomial stuff that we talked about in last week's material. The normal distribution stuff is the first 3 options. Now, actually, we don't use the first option ever. It's called NormalCDF. That function right there, we use that when we want to draw the picture of the normal distribution on the calculator. I'm not a big fan of using the calculator to draw the picture, only because I feel like the calculator is too accurate. And yeah, sometimes being too accurate is a pain in the neck because it's hard to see the shaded regions. These shaded regions sometimes are really tiny. And if you use the calculator to draw them, it'll draw them super accurate. You won't even be able to see the shaded region. So what I like to do is I like to draw them by hand and shade so that I can see it. All right, so then what options are we going to use? Well, right now we're going to make use of NormalCDF. This is this table right here. And this third option, which is called inv norm, we're going to make use of that too, but I'll do that in a separate video. These features are also described in detail with examples and screenshots in the textbook as well. All right, so let's talk about this normal CDF operation and how you use it. All right, so first of all, notice if I select, I'm going to go on top of 2, normal CDF, and hit enter. Notice what it does. It brings it back to the home screen, and now it's blinking. Obviously, it's waiting for me to tell it what I want. Now, I have the old version of the TI-84. Some of you guys might have the newer version. You'll know right away if you have the new version, because when you do this, it doesn't bring this normal CDF command back to this home screen. I believe it says lower, upper, mean, standard deviation. It's like a little list, and you just have to tell it what you want. So if you're like me and you have the old version, then you have to know how to use this. So what I'm going to do is I'm going to come over here and write out how to use it. All right, so the normal CDF. You have to input this in this order. If you don't input it in this order, what ends up happening, it'll give you a wrong answer. So the first input it needs is the lower bound of shade, followed by a comma. All right, so what does that mean, the lower bound of shade? When you look at the shaded region, there's a boundary on the left-hand side, and there's a boundary on the right-hand side. In other words, two numbers that describe from what number to what number is this shaded region. All right, so the first input it needs is the lower bound of shade. The second input it needs is the upper bound of shade. So I'm going to kind of keep this in line. Then a comma. And then it just needs the mean and the standard deviation in that order. So mean, comma, standard deviation. And then you close the parentheses. That is 4 inputs. The lower bound of the shade, the upper bound of the shade, the mean, then the standard deviation. Now remember, for the standard normal distribution, the mean and standard deviation are always 0 and 1 respectively. They're not always 0 and 1. They're just 0 and 1 when we're dealing with z-scores, which what we're doing right now. As you're going to see, these aren't going to be z-scores for very long. Next week's material is going to involve applications, and those are going to be raw scores, and then the mean isn't going to be 0 anymore. It'll be some other number, say like 10 or something like that. All right, so let's talk about what these values would be for this particular scenario. All right, so this normal CDF. So let's talk about the lower and upper boundaries. Now, this is going to annoy you a little bit. It's going to annoy you because, the people at Texas Instruments, what they've done is they have their own lingo. And, we have to deal with that, unfortunately. So notice this shaded region, the lower boundary, there isn't one because it shades to the left forever. So in theory, the left bound goes to negative infinity. In other words, the smallest negative value you could think of. So now, obviously, we have to have a way of telling, the calculator what negative infinity is. And actually, it does. The calculator doesn't understand infinity, first of all. It's a machine. It counts to a number. And it is the biggest number it can count to. And when you try to make it count bigger than that, it crashes. The biggest number this calculator can count to is just shy of a googol, which is, in this calculator, it's written as E99, which means 10 to the 99th power. So how we type it is E99. But it's negative infinity. So you type negative E99. Now let's just talk about what that means so you understand. The E means 10 to the, like an exponent. So 10 to the 99th power, which is a 1 with 99 zeros after it. But that negative means negative that number. Now where is this little E right here? How do you get it? Actually, it's above the comma key. So above comma, it says EE right here. And I know it's blurry it's because it's light blue and it's really tiny. It's hard to see, but this thing doesn't get any bigger, unfortunately. But above the comma key, it says EE. That is the number. So if to type negative E99, you have to hit a negative sign, which is down here at the bottom. And then you got to hold second comma. Notice it puts that little E. That's the E to, that's scientific notation for 10 to the. And then you have to physically type 2 nines. Now that, for the calculator, is negative infinity. So what do I want? I want to shade from negative infinity all the way up to and including 1.73. So I'm going to type a comma because it's lower bound of shade followed by the upper bound of the shade. Well, the upper bound of the shade is 1.73. So I'll type in 1.73 followed by a comma. And then all I need next is the mean and standard deviation. And for the standard normal distribution, they're always 0 and 1. And close your parentheses. So what does that statement say? You're saying, give me the area under the normal distribution between this number and this number, between negative E99 and 1.73 z-scores when the mean is 0 and the standard deviation is 1. Now listen, we did it. It's 0.9582. We looked it up in the table. This better tell me that number. All right, so here you go, 0.958184901. Obviously, the calculator's answer, way better than, the old-fashioned, century-old or what have you table, which is only 4 decimal places. So once you round this answer to 4 decimal places, you can see that 8 right there tells that 1 to go to a 2. All right, so clearly this normal CDF operation, once you get good at it, which you will, you'll get real good at this operation. You're going to use it all the time throughout the course, trust me. You're going to get really fast at this. And, if you have the new version of the calculator, it asks you lower bound and then upper bound. I think it actually just says lower upper. So you'll know if you have the new version of the calculator. And then you don't have to worry about that order right there because it just picks your brain. It says lower, upper, mean, standard deviation. You pop the numbers in and you get the value. All right, so notice, this table only gives area on the left. But since you can specify lower and upper bound, well, then you could ask it this question as well, the second question, from 1.73 to infinity. All right, well, think about that. First of all, let me finish typing this expression because I never did that there. So that's going to be comma. This is 1.73, comma 0, comma 1, right? So let me finish that normal CDF statement off because I forgot to. All right, so I'm going to copy this thing and paste it down here to help me out a little bit. It'll speed things up. And I'm going to leave that 0 and 1 in there. And let's talk about the first couple of entries of this statement. Well, notice now this shaded region, the lower boundary, the left-hand boundary is 1.73. All right, so in my statement over here, that'll be 1.73. That's my lower bound of my shaded region. Now my upper bound of the shaded region, now what is it? Well, technically, this shade goes on for infinity, right? So there isn't an upper bound. All right, so what is that upper bound technically? Well, technically it's infinity, but this time in the positive direction. So that's positive infinity. Now to type negative infinity, we wrote negative E99. So to type positive infinity, we're just going to type E99. So this will be E99, and of course, comma 0, comma 1. So we're saying start at 1.73, shade the forever, when the mean is 0 and standard deviation is 1. All right, so I'll again go to the calculator, and you go second bars, choose option 2. Remember, we don't use option 1 in this class. I'm not going to use it. So option 2, so that is 1.73, comma, E99, comma 0, comma 1. All right, hit enter. And there you have it, 0.0418, just like we got when we did it by hand. Now, naturally, once you have this answer here, you're not typing any kind of normal CDF statement to get this answer. I mean, you're just going to use common sense at this point. What I'm doing right now is showing you, that second question as if it were a standalone question. What would you do? How would you work that problem? Using the calculator rather than having to go to the table. Now, you may say, well, you know what? I like the table better right now. It's visual. Yeah, I know you like the table maybe a little bit better right now, but trust me, in the long run, the calculator is going to be faster for you. Even though the calculator's function is a little weird because you have to, remember the syntax, lower, upper, mean, standard deviation. Trust me, in the long run, the calculator is going to be the way to go because there are other features that this thing does, NormalCDF, that we're not seeing right now. All right, so just to rehash, infinity in the calculator doesn't exist, so we have to fake it. We use E99 or negative E99, depending if you're shading to the left or shading to the right. One other thing I guess I should point out to you about, the general E99 business, I think it's kind of funny. Like, for instance, this answer, which is 0.0418, right? Which the answer, that was from shading from 1.73 to infinity. Watch this. Watch what happens if I bring up that last statement, and I'm going to change that E99. I'm going to change it to 100. Now, I think you all understand the difference between, a Google and 100. We're talking like, grains of sand at Jones Beach here, right? Take 100 grains of sand out of all the grains of sand at Jones Beach. That we're starting to get close to these, the magnitude of these numbers. Me changing this from, E99 to 100 is a big change. But check it out when I hit enter. It's the exact same answer, which is kind of weird. You're like, wait a second, from 1.73 to infinity or 1.73 to 100 and I get the same answer? Yeah, I mean, it's kind of weird. But then you say, well, what if I change that to, like 50 or something like that? What'll happen then? If I go here and change this to a 50. So what I do now, 1.73 to 50. And you're like, wait a second, that's the same answer. How low can I go here? Let me go down to 25. Shade from 1.73 to 25. All right, this is getting ridiculous now, right? It's the same frigging answer. All right, let's do it again. I'm going to go to 10. So now, instead of shading to a Google, I'm shading to 10. Look, I mean, now it's getting ridiculous. Look, I still have the same answer. So then you say to yourself, what's going on here? Why is that the same answer? Well, you know why it's the same answer. Because according to the empirical rule, when you walk out from the center, when you're at 0, and you walk out 3 standard deviations to the right and 3 standard deviations to the left, you capture 99.7% of the data. So in other words, this area, if you change that 1.73 to a 3, you're catching 99.7% of the area, of the 1 in other words. So how much area is really out there in the long run? Well, once you're past 3 standard deviations from the center, not a heck of a lot. So what a lot of people do, instead of this E99 business, because it kind of aggravates people, instead of going 1.73 to E99, you just pick some ridiculous number out there, like 1,000, and make life easy for yourself. But that's just a matter of preference, and I'll leave that up to you. I know if you go to the Math Center, they'll always tell you to use E99, but to me it's a common sense thing. If we're talking about the highest test score, and we're taking an SAT, the highest SAT, say, on the math section is 800. I'm not going to put E99 right here. That wouldn't make any sense, E99, because you can't get E99 on the math SAT. The highest I can get on the math SAT is 800. So I would use 800. To me, something common sense. But that's totally up to you. All right, so the beauty of this calculator feature is once you get good at it, you'll be fast, and these questions will fly. So in general, what should you see here? You should see a statement in words, the translation of that words into mathematical symbols, shading in a region under the bell curve, and then using either the table or your normal CDF operation in the calculator to work that area. And notice when we worked it with the table and we worked it with the calculator's normal CDF feature, we got the same answer, although the calculator solution is more accurate. So in the long run, the calculator answer is a little bit better. Okay, so you really have to read the chapter on this. So the material where all this is spoken about is actually in section 7.5 in the textbook. All right, so make sure you check that out. Read through that stuff carefully. There's a lot of calculator examples showing you how to use this normal CDF feature as well as detailed explanations such as this. But I think it's important to kind of hear someone talk about it so you can see how somebody else thinks about it rather than just reading it out of a textbook. It kind of helps you out a little bit more. All right, so if you have any questions, shoot me a message in Blackboard, and thanks for watching.